The efficiency of a vapor power cycle is net work output by heat input. So, to increase the efficiency, we can either increase the net work output or decrease the heat input. One way to do this is to increase the pressure and temperature at which water enters the boiler. This way, the amount of heat needed decreases as the length of the line 1 to 2 decreases, and at the same time, the work output from turbine, represented by the line 2 to 3, increases. But as we increase the pressure and temperature, the dryness fraction of the output of the turbine will decrease. That is, the steam will be more wet and have more water content. If the dryness fraction becomes less than 0.88, it will result in corrosion and rust formation inside the turbine. So in order to solve this, we found that if we reheat the output of the turbine, and then run it through another turbine, then the final steam output becomes less wet and will not cause corrosion. This is called the Rankine reheat cycle. For the reheat process, we run the output of the high pressure turbine through the boiler. This raises the temperature at a lower pressure. The reheated steam is then run through a low pressure turbine. Altogether, we have 6 processes now. Heat addition in the boiler from 1 to 2A, work extraction from high pressure turbine from 2A to 2B, reheat in the boiler from 2B to 2C, work extraction from low pressure turbine from 2C to 3, heat rejection in condenser from 3 to 4, and work input in the pump from 4 to 1. We can determine the heat and work values at each step, using the specific enthalpy from HS diagram. For the pump, however, we usually calculate the work done as specific volume times the change in pressure, since the enthalpy of subcooled liquid is difficult to find. We can calculate the net work done as the sum of work delivered by high pressure and low pressure turbines, minus the work done by the pump. Similarly, net heat input will be the sum of heat input in boiler for initial heating, as well as the reheating. Taking the ratio of these two, this is the equation for efficiency of a Rankine reheat cycle. We can substitute the enthalpy values for each process to get another form of this equation. If we reheat the steam, we can compare the increased work output with the work output that we get without reheating. This is called the reheat factor. The work output with reheat is the sum of the cumulative enthalpy drops as the steam passes through the different turbines. That means the enthalpy drop from 2A to 2B, plus the enthalpy drop from 2C to 3. The work output without reheat is the enthalpy drop we would have had if we did not reheat, and instead directly output steam at a point 3 dash. So, it is the enthalpy drop from point 2A to 3 dash. This is how we calculate the reheat factor.